Hi, and welcome to a lesson over right triangle trigonometry today. We'll try to cover some of the basics. We'll use right triangles to evaluate trigonomic functions. We'll talk a little about 30, 45, and 60-degree angles, um, and use definitions of trig functions at any angle, and then use right triangle trigonometry to solve applied problems. So I want to ask you guys, how do you think we could calculate the height of Mount Everest without actually climbing it? So you may already know the answer to this, but if not, we could do this using something called trigonometry, which is what you guys are in right now, but also, or specifically, right triangle trigonometry. So that's what we'll be doing today is finding sides or side lengths of right triangles using trigonometry. So in this diagram right here, I just want to talk about it for just a second so you guys can make connections to what we already know and what we're about to know. So here you may see that this is kind of part of a circle. So if I finish this picture, we would have that full circle, right? And then we would also be on a coordinate plane. So if you're wondering, well, why is this labeled X? That's not the full X-axis right there, and same thing with Y. You're right. What we've done here is we've drawn a right triangle, and then we've connected it over here to our circle. And you notice that our hypotenuse is 1, and the hypotenuse in this situation would also be the same as the radius. So last class, we were going around the circle and finding the degrees and the radians of different spots. Well, today we'll be working with right triangles, and we'll eventually be able to find sine, something called sine, cosine, and tangent of those specific angles. And so right here, again, back to my radius of 1, if I connect down to that x-axis, and then I go across until it meets, I form a right triangle. I have my angle T, but up here, at this point where I hit the circle, I just created basically like an ordered pair. So I'm just going to keep that in the back of my mind. We'll come back to that later. So just the basics here of a right triangle. Of course, you guys recognize the hypotenuse because that's something we learned before. So the opposite and the adjacent side are going to be relative to our angle. So in this case, we have angle T, and the opposite side will be whatever is opposite of T. And then the adjacent side, adjacent means it's kind of sitting next to something or closest to that angle, will be sitting right there, like next to the angle. So here are your vocabulary terms down here, and I'll just give you the official definitions. A hypotenuse is the side of the triangle opposite of the right angle. The adjacent side is the side closest to the angle, and the opposite side is the side across from that angle. So those will be important vocabulary terms throughout this lesson. Now we'll jump right into it. How do we find trigonomic functions on a right triangle? Well, the trigonomic functions can be found using ratios of the sides. So just like we had that triangle just a while ago, you guys know that we had different labels for each of those sides. And now what we'll do is just use the ratios and assign them a trig function. So the first one is called sine. But when we write it as a function, you're just going to see S-I-N-T. It doesn't look like sin, but its actual name is sine. And this ratio is the opposite side over the hypotenuse. Cosine which you'll see is just like cos, right? But it said cosine of t, that angle, is equal to the adjacent side over the hypotenuse. And then tangent of t, is equal to the opposite over adjacent. So if you're having a tough time remembering that, we use this very common mnemonic for remembering these. Excuse me. And that mnemonic is called SOHCAHTOA. And basically, you're just saying all of those ratios at once, right? But just the first letter. So S would stand for sine, and then O would be opposite, and H hypotenuse. So you guys can kind of see how this mnemonic works. See, sine was opposite over hypotenuse. Cosine was adjacent over hypotenuse. So there's adjacent over hypotenuse. And then tangent was opposite over adjacent. TOA. Pretty cool, huh? So when you're trying to find these, you can kind of repeat that to yourself, or you're welcome to just write those all out. Let's go to our first example. So how do we use these trig functions? So first of all, we're given this triangle, and let's notice what we have. We are given the three sides. I have 17, 15, and 8. But what we're missing is, this one is called alpha. So if we're missing alpha, then we're going to use one of our trig functions. And the way I choose depends on the information that I'm given and what I need. So in this case, I know that I have all of the sides, so I can use any of those that I would like. But since I'm looking for this angle, I know that maybe I could use the adjacent, right? And the hypotenuse. And why do I want those? Well, I'm using cosine. So remember, cosine, and in this case we're saying alpha, is equal to adjacent over hypotenuse. So my adjacent side will be 15, and the hypotenuse is 17. Now, all I do is just use that information for my ratio. So the adjacent side will be 15 divided by the hypotenuse, which is 17. So that means that cosine of alpha is equal to 15 over 17. That's my answer. Now, in addition to these functions, sine, cosine, and tangent, there are 3 more functions, and these are just their reciprocals. So I tried to write this out so you guys could see it laid out all at once. Let's say, for example, we're looking at sine. Well, we know that sine is opposite over hypotenuse. So if I look at the reciprocal, all I do is I flip these, right? And then now I'm left with hypotenuse over opposite. And what that's called, when I find the reciprocal of sine, that is called cosecant. And cosecant can be written as hypotenuse over opposite, or 1 over sine t, because again, it's the reciprocal. So I'll just do 1 over sine t, either one of those. So then at the end here, this is just saying that sine is equal to 1 over cosecant t. So we can go either direction. Cosecant is equal to 1 over sine t, or sine t is equal to 1 over cosecant. So first, cosine, that ratio is adjacent over hypotenuse. If I find the reciprocal, I get hypotenuse over adjacent, and that is called secant. And I can also call secant 1 over cosine t, or we can call cosine t 1 over secant t. And then finally we have tangent, which is opposite over adjacent. Its reciprocal would be adjacent over opposite, and we call this one cotangent. So cotangent is 1 over tangent, or we can say tangent is 1 over cotangent. Whew, I know that's a big mix-up, but it is important to note that we have some reciprocal functions. So here's an example using a reciprocal function. So we're going to find secant A. So go back, we say, secant is the reciprocal of cosine. Since cosine is adjacent over hypotenuse, then secant is hypotenuse over adjacent. So secant of angle A is going to equal hypotenuse over adjacent. So now I need to label my sides so I know what's what. So here's my right angle. That means this is my hypotenuse. I was given angle A, so the side opposite of that angle is called the opposite. And then the side closest to that angle is called the adjacent side. So I need this one and this one. Whoa, I ran into a small problem. What's my problem? I don't know the hypotenuse, but I do know something called the Pythagorean theorem. And that's also an important aspect of right triangles. So here, what I do know, and I can label these either side, A or B, I have 6 squared plus 13 squared is equal to, and we'll just call it c squared for now because I don't know my hypotenuse. So I go ahead and I add these together. So 36 plus 169 is equal to c squared. That gives me 205 is equal to c squared. So to find just c, I need to take the square root of each side. So I found the hypotenuse is equal to the square root of 205. So now I can set this up. Square root of 205 over adjacent, which was 6. So there's my answer. Secant A is equal to the square root of 205 over 6. Now, quickly, I'm going to review special right triangles because this might make our process a little faster when we're working with right triangles. So first of all, there's something called a 45, 45, 90 angle. So if we think about it, triangles have a total of 180 degrees. So if I add 45, 45, and 90, I get 180. This one is special because I can find its sides fairly easily by using the Pythagorean theorem. They'll have always the same relationship. So since these two angles are the same, those two sides will be equal. So A and A. So what if I was trying to find the hypotenuse? Well, I'll quickly use Pythagorean theorem. And instead of a squared plus b squared, I'll use a squared plus a squared since they're both the same. So this will give me 2a squared. So now to find out what c is, I take the square root. So I'll be left with the square root of 2a squared. So remember when you're using square roots and you're multiplying under the radical, you can split those square roots up and it can look like this. And I want to do that because one of these is a perfect square and one of these is not. The square root of 2 is not a perfect square, but a squared is, meaning the square root of a squared is just a. And since that might look a little confusing, I want to just say a square root of 2. So the hypotenuse, or c, is equal to a square root of 2. And I need my pen back. There we go. So that's the relationship of the 45, 45, 90 triangles. And what about 30, 60, 90? So again, these will also have the same relationship. We'll call this side A, and we'll call this side B. And then we're going to call this side, well, we don't know yet, right? So we have to figure this one out. So again, using Pythagorean theorem, I don't have much information right now, but what I do know is something kind of cool. If I go ahead and I make another one of these, what do you guys notice? Well, this would be 30, and so would this. So that whole angle would be 60 degrees. Remember we said that a triangle can only have 180 degrees? So that would also have to be 60, meaning that down here on the bottom, these would each be A and A. So since all the sides are the same in an equilateral triangle, this would have to be 2A and 2A. Well, that was my hypotenuse before. So now that's going to be C. So now I have a nice little problem to work out. I have some variables I can combine and some squaring. So first of all, 2a squared will be 4a squared equals a squared plus b squared. Let's go ahead and combine the a squared terms, leaving us with 3a squared. Now, oh, and I think this b was still squared. So now I need to take the square root of each side. Same idea as before. I can split that square root of 3 and that a squared up. So a squared is, or the square root of a squared is just a, and then square root of 3 is equal to b. Huh. So what did I just figure out? I just found out that on a 30, 60, 90 right triangle, my two sides I can label a and b, and the relationship of the hypotenuse to one of those sides will be 2 times a. So this is just a quick view of this first one is the 45, 45, 90 triangle. So if I'm at 45 degrees here, that we also know as pi fourths. So it works the same in radians as well. And then over here, this is at, I think this one is the 60 degrees. And so we're at pi sixth. Okay, perfect. So now let's find the lengths of sides A and B on this triangle, just using kind of what we know. So we have 14, and we know that this is a 45-degree angle, and we're asked to find the rest of it. So what do we know? What do you guys remember? Well, we also have a layer of information that we just learned today, which is the sine, cosine, tangent. So if I wanted to find the side lengths by thinking about what we have, so we're given the hypotenuse, and we can call either one of these, I mean, we can use either side we want. So we're not set to a specific trig function right now, but I think I want to go ahead and just use sine because I have hypotenuse and I have a. So remember that sine of a given angle is equal to opposite over hypotenuse. So in this case, I have sine of 45 degrees is equal to a over 14. That's what I know so far. I can actually find out what sine of 45 degrees is, or we can solve this out by using just basic algebra and a calculator. So the difference is whether I need a decimal answer or specific answer. So I'm going to go ahead and show you guys this specific answer just because I think it's important to also know this as well. So I'm going to go off to the side here, and we're going to find out what sine of 45 degrees is. So I'm going to take you guys back to our standard position, 45 degrees. Oops, not 450, 45 degrees. So I hope you guys recognize this and you guys are remembering like, oh, the big circle and all those angles that go around. So if this is 45 degrees, remember we said this is a 1 unit circle, so that radius right there would be 1. If I formed a right triangle, then I would now call this side x and this side y. Well, what I know about this is that the radius is equal to 1. And just a second ago, we talked about special right triangles and said that with 45-degree right triangles, the hypotenuse is the relationship between the hypotenuse and the other sides is that the hypotenuse is supposed to be a squared of 2, and these sides are a and a. Well, since I know that the radius is 1, that's also my hypotenuse. I'm going to say 1 is equal to a square root of 2. Now, if I can find a, then I will find the two sides, x and y. And I know that they're equal because this is a 45-degree angle. So now I go ahead and solve, and I end up finding that a is equal to 1 over square root of 2. So remember, when we deal with radicals, we want to keep the square root of any number out of the denominator. So I can multiply this by square root of 2 over square root of 2, and I get square root of 2 over 2. So sine of 45 degrees is equal to square root of 2 over 2. So why did I do all that extra work? Well, now that I know that these are the same and I have those two answers set equal to sine of 45 degrees, I can set my two answers equal to each other. And then now I can find out what A is. So we can do this a couple of different ways. If you're really good with ratios, maybe you'll notice like, hey, right here, all I have to do is divide by 7. So right here, if I divide by 7, or I can do that. If I divided this by 7, then this needs to be larger, right? If that's not working, then let's just use cross multiplication and division. Okay, so let's say a times 2, so 2a is equal to 14 square root of 2. So now I can solve this out pretty easily by, I'm just going to divide both sides by 2. And I end up with a is equal to 7 square root of 2. So I found my side. Both of them, a and b, are 7 square root of 2. Okay, so now we'll go and use trig functions to find a missing side. And it's kind of like what we just did. So you're going to select your trig function by looking at what you know, set up your equation, your ratio, and then solve for the missing side length. So here's our example. We have a 60 degrees angle that's given to us. We know that this is a right triangle. It's flipped, so we have to be careful when we look at our sides, but C will still be the hypotenuse. And since this is my angle here, 10 is going to be the opposite. And A will be, we can use that one as our adjacent. Okay. So we're going to solve for A and C. So how do I do this? First of all, I think I want to use sine because sine is the ratio of opposite over hypotenuse. So we're going to use sine of, I'll just call it theta for now, is equal to opposite over hypotenuse. So now if I do that, I'd say sine of 60 degrees is equal to 10 over c. And I'll go ahead and set this up. So to solve this, I'll solve it just algebraically. So when I find out what c is, I can multiply c on both sides to get it out of the denominator. And now I'm left with c times sine of 60 degrees. And this looks daunting right here, but this is just a number I could stick in my calculator. So don't worry about that. Is equal to 10. Now to find out what that is, I'll divide by 60 degrees on both sides, sine of 60 degrees. Okay, so when I go and I find this, I need to do something like before. So what would sine of 60 degrees be? I think I'm actually going to go use a separate sheet of paper. Okay, so I'm going to review our special right triangle that we just talked about. So a 30, 60, 90 degree right triangle would look something like so. So I have my right angle. This side, the hypotenuse is 2a. We said this side is a. And I actually left out something before. I called this side b, but that side would actually be a square root of 3. And I think I found that in the last slide and I forgot to circle it and write it down. So b is a square root of 3. And that's important because now everything is relative to a. So what we're trying to do is find sine of 60 degrees. Okay, so going back to our angle in standard position, say I'm right here at 60 degrees. So this is my terminal side. This is my initial side, and there's my angle. And I'm going to find out what sine is by using that information I gave you guys at the very beginning. So remember that very first slide where we said that on this circle, those points can be made by basically having like x and y coordinates. So we'll call this horizontal side x and this vertical side y of my right triangle, and my hypotenuse will be 1. So let's just say I want to find x. X is going to represent cosine, and y is going to represent sine. And the reason is because of their ratios here on this drawing. So let's go ahead and try to find cosine first. So we'll need to know that one anyway. Kind of like what we did with that 45-degree one a while ago. I know the hypotenuse is 1. So I'm going to set 1 equal to what I know about this special right triangle. And I know that it's supposed to be 2 times a. So this is going to help me find out what a is. So a is equal to 1/2. So if you guys kind of look at my picture here, it's backwards. So a is actually the same thing as x. And then to find y, now I can use this part of the special right triangle, which is a square root of 3. So since I know what a is, it's going to be, so I'm going to say y is equal to a square root of 3. And we know that a was 1/2 square root of 3. And I can leave it like that, but I kind of like to put it like this so I can see my denominator easily. So this would be square root of 3 over 2. And I also found cosine. So that's 1/2. Remember we said cosine would be the first one. And sine would be square root of 3 over 2. So if I want to know what is sine of 60 degrees, it is square root of 3 over 2. So now let's go back to the problem that we were working on. And now I know something. Sine of 60 degrees is square root of 3 over 2. So that was the non-calculator way of finding that answer. Can I just type in sine of 60 degrees in my calculator? Absolutely. It will give you that answer in decimal form, and you can still use it, but you just won't be able to know that it was, that it looked like this. It'll just look like a decimal, okay? But yes, you can. So now I have this, so I need to figure out how to do that. So 10 times 2 over square root of 3, and that will equal 20 over square root of 3. So I just found the hypotenuse. So C is equal to 20 over square root of 3. Now to find A, you need to use a different ratio. So I'm going to use tangent to find A. So this was C. Now we're going to try to find A. So to find A, let's say tangent of 60 degrees is equal to, and tangent is opposite over adjacent. Okay, so my opposite side is 10. My adjacent side is A. And I'm using this because I'm trying to find the unknown. So I'll do that algebra. A times tangent of 60 degrees is equal to 10. Okay, so then now I'm going to divide tangent of 60 degrees on each side. And I end up with A is equal to 10 over tangent of 60 degrees. So what is tangent of 60 degrees? I'm going to go back to that page.